Welcome to AP Chemistry at Honolulu High School. I'm BBrown, and in this movie we'll be getting a little extra help for the Chapter 15 Equilibrium test. Now, as before, when we've looked at these things, I try and look at some of the most missed conceptions and ideas, our concepts and ideas in math problems from the previous test. And I've noticed that there's icebox problems, especially when you're given KC. So when you have to deal with X, students tend to have more of a difficulty there. Stoichiometry and rate. Now this is really related to a concept from last chapter. Remember, equilibrium is all about rates. So our ideas from last chapter don't go away. And then finally, some things related to Chateliers Principle. Some things students do well, some things students tend to struggle with a little bit more. So those are the three main things we'll be looking at. Now the first situation here is icebox problems when given a KC. So at 200 degrees Celsius, the equilibrium constant Kp for the reaction is given as 2.40 times 10 to the third, and then they give you the reaction. Now I'm going to rewrite the reaction out here because one of the things we need to really do is understand what's going on with icebox here. So let's say that's our reaction. So what's going on initial, change, and at equilibrium. Now it says if I pull information out, besides the fact that it gives me a Kp, which we'll come back to, it says a closed vessel is charged with 36.1 atmospheres of NO. So we know this is 36.1 ATM. Now, if we're putting into an empty vessel 36.1 atmospheres of NO, that means we initially have 0 of those. Remember, this is an idea that's an important concept to really get. Otherwise, this problem will be very, very difficult. Now, as we reach equilibrium, since we had all reactants, obviously we're going down by X. But notice, there's a 2 there. So I don't say down by X. To make this easier to relate to my other situations here, what I'm going to do is I'm going to say this is going to go down by 2X. And therefore, this will go up by X, and that will go up by X. Because as the stoichiometry, and this is something we'll get into a little bit in the next problem too, as the stoichiometry suggests, we're going through NO at twice the rate we're producing N2 and O2. So if that one goes down NO by 2x, then N2 and O2 will go up only by x. So when we put these together, I know at equilibrium, these will have a concentration of x, and this will be 36, if I can write 36.1 ATMs minus 2x. So I know at equilibrium, that's how much of this thing's concentration would be in terms of x. Now, once you've got your icebox set up, the next thing you need to recognize is you need to have a K expression. Since we're talking about pressures here, this is Kp. And in Kp, remember, we don't use brackets, we use parentheses when we're talking about pressures. So it would be the pressure of N2 times the pressure of O2 over the pressure of NO squared. And that's going to equal our value of Kp. Well, in this particular problem, they told us that Kp was 2.40 times 10 to the third. So I'm going to write that as 2400. Just remember we have 3 sig figs here. And that's going to equal our equilibrium concentration, our pressures of N2 and O2. Well, those are both x, so on top we're going to have x squared. And on the bottom we're going to have 36.1 minus 2x quantity squared. Now, one of the reasons I picked this particular problem is because I want to highlight something that students miss at this point, because we've talked about the concept of going to quadratic. So yes, you should be prepared to use the quadratic equation. No, you don't have to memorize it. I'll have it written on the test for you to use if you need it. And yes, on one question you will need it, and only one. You should be prepared to use the quadratic, but look for simple solutions to that. In this particular case, I've got an x squared over a quantity of 36.1 minus 2x squared. Well, to avoid the quadratic, how can I do that? Well, if I take the square root of this side, I'm going to get rid of my squareds, and I just need to take the square root of that side. So to simplify this problem, it's going to be the square root of 2400 is going to equal x over 36.1 minus 2x. Now at this point, I can much more easily solve for x without having to go through the quadratic equation. So look for squared on top and squared on bottom situations. We can simplify the math and avoid the quadratic. Now, in this particular case, we would then solve for x. And at that point, we could then know what each of these concentrations would be at equilibrium by plugging it in. So technically, in most problems where they're giving you the K value, what they're asking you for is typically what are the equilibrium concentrations of either one or all of the different substances. So you need to be aware if you're given a K, this is probably what you're doing. And this is where the quadratic equation could rear its ugly head. But look for the situation like in this case where we end up with a square over a square situation where we can avoid that. So this is one of the most common icebox issues people struggle with is when we have values for x. And that's going to happen when they're giving us a k value. Now, if they don't give you a k value, that's what they're going to be asking you to find. And in those particular problems, you'll notice with what's given, you'll be able to figure out what x is. So then you can figure out what your equilibrium concentrations are based on that. So what they typically do is instead of one of these being an unknown, they will tell you what your N2 concentration is at equilibrium. So if they tell you this is 2.8 atmospheres, now I know what my X is, and I can figure out what this is going to be in actual numbers, and this is going to be in actual numbers. Because in this case, it would be 2.8 and 36.1 minus 2.8 times 2. And then from there, I can easily calculate what the K value is. So if they're not giving the K value, typically they're going to give you information so you can find your X in your icebox situation. So it's usually a much easier problem. Students have much less difficulty on that. Where they tend to struggle is this type, where they give you the K value, which means you're going to be dealing with X's. Next situation I want to look at is stoichiometry versus rate. So I want to look at a time and concentration situation here and remind you of the tie between stoichiometry. Now this is something we routinely use in our icebox relationship when we look at how much something is changing. So in the icebox, people have no trouble with it, but when we look at it from this point of view, people tend to struggle with this idea. So notice over this time interval here, this changed by 2.0 molarity. Well, based on the stoichiometry up above, A is changing twice as fast as what B and A2B are changing. So if A is changing by 2.0, I would expect B to only change by 1.0. So I should be able to predict that that's going to be 4.0 at that point. And the same thing with relationship to A2B. As fast as B is going down, A2B is going up by the exact same amount. So if B changed by 1.0 molar, I would expect A2B to go up by only 1.2 molar. And I can do that over each time interval. Notice here it's 1.0, so I'd expect my difference here to just be 0.5. So I would expect that to go down to 3.5 and this to go up by only 0.5. So that's an idea that it's a concept out of last chapter, and it's related to what we do when we set up ice boxes. We talk about changing concentrations and how this change in concentration is related to that change in concentration through stoichiometry. Sometimes students forget to apply it here or to work backwards. We can actually look at our change in concentrations and determine what our stoichiometry has to be. Just like if we look at our ice box and we actually know the values for the change in x, we could be able to determine what the coefficients of the balanced equation would be as well. Now, last issue I want to look at here is Chateliers Principle. So notice I've got a colored gas system, red and blue, because red and blue are very similar to a demo I did in class. And you get that if it's red, then that must mean the reactants are heavily dominating equilibrium position, and therefore we have very little or blue gas in there. If the reaction system is blue, that means we've got products being heavily favored. And if it's purple, then we're somewhere in between. We've got mixes of the two. So this is a nice one to look at what's happening with equilibrium situations because we can tie it to a color change. So if increasing the temperature turned the container from blue to red, is the reaction endo or exothermic? Remember, increasing temperature favors the endothermic direction. So either the forward or the reverse here is going to be an endothermic direction. And notice it says it changes it from blue to red. So if we're going from blue to red, obviously we have an equilibrium shift towards the left, towards the reactants. So that means our product concentrations are going down and our reactant concentrations are going up. Well, Where would energy have to be to do that? So let's look at, say energy was over here. So let's just pretend energy was over here. Well, that would mean the forward reaction is the endothermic direction. Increasing temperature should shift it that way, not the direction we just looked at. So we know energy can't be over there. So let's take a look at energy on this side. Now would that make sense? Well, if energy went on the right, the endothermic direction would be the reverse, and increasing energy would shift equilibrium to the left. That exactly explains what we're looking at. So energy must be on the right side here. And when energy is on the right, that's an exothermic reaction. So it makes sense, based on what we're given, that this has to be an exothermic reaction. Energy would be on the right. So that's one thing that students struggle with is this, because it's not just simple left-right. You have to apply what's happening to figure out what a left-right would mean. Now, let's take a look at the bottom situation here. Under what conditions would you increase the yield of B? Once again, this is not such a simple left-right question. You've got to figure out what's going on left-right in terms of a shift and apply that to the situation. So it's a little more complex. Now, the goal in this case is to increase the yield of B. So that means we want to make more of this substance. So what can we do to get more B? Now, besides playing with concentrations here, so yes, I could add more A2B. So, but if it's a closed system, I can't do that. But yes, increasing the amount of A2B would allow me to have more A2B collisions, reversing the reaction, making it more likely that I would get more B. But remember, this is a closed system. So really all I can do here is play with energy, or potentially if my closed system is like a piston, I could play with pressure and volume to try and get more B. So what could I do with temperature to get more V? Is it low or high temperature? So let's look at this from a temperature point of view first. Now notice we just established energy was on the right, so it's an exothermic situation. Well, if I want to make more B, that would be an increase the temperature, increase the energy type situation. So high temp would shift equilibrium to the left and give us more B. Now, from a pressure volume point of view, so let's say this was a reaction system that was like in a piston, and we could easily change our pressure or our volume. Well, looking at it from a volume point of view is easier, but we could also talk about it from a pressure point of view as well. Now, notice what our delta N is up here. So in order to get delta N, we're comparing what's happening with gas particles. On the left, both substances are gas, and we have two A's and one B, so it's a total of 3 moles of gas particle on the left. And on the right, it is a gas. We've got a total of 1 mole there. So our delta N here is actually a -2. So we're decreasing in the number of gas particles. So if we knew what the Kc is of this particular reaction, we could take our T to the -2 and we could calculate what the Kp was. That's not where I was going with this problem. What I'm looking at here is just a simple, would increasing or decreasing the volume, should I pull up on the plunger or push down the plunger to get more B? Well, notice there are more gas particles on the left. So if I am decreasing the volume by pushing down on the plunger, that's not going to favor the side of the reaction that produces more. It's going to favor the side of the reaction that produces less. So what do we want to do with the volume here? Well, I certainly don't want to decrease it. That would shift equilibrium to the right. So what I would like to do is increase the volume or decrease the pressure. It would end up doing the same thing. So those are really the conditions that would allow me to produce a higher yield of B. So what we're looking at here is not just simple straight left-right, but other things where you have to think through what happens with the left-right shift in order to accomplish what it is I'm looking at. And that naturally makes it a little bit more difficult. Now, the next thing I wanted to look at related to this chapter was some of the key math and concept questions really on the test. And we did this on the last test. And we're going to do this breakdown for most of the chapters in second semester. So let's take a look at some of the math and concept ideas you need to understand. First off, equilibrium conditions. Make sure you understand what conditions must be met in order to be at equilibrium. And this is something that's on page 300 or 630 in your notes or in the textbook. And remember, we also looked at this in your notes as well. And also understand what's constant, what's equal at equilibrium. That's going to come later. But as far as a math and concepts idea, that's definitely something you should understand. Next thing, you should be able to write equilibrium expressions. either Kc or Kp. Remember, they're the same equation. The difference is whether we're talking about concentrations or whether we're talking about pressures. And that means whether we have brackets for Kc or whether we have parentheses when we're talking about Kp. So know when to use which. Also understand homogeneous equilibrium versus heterogeneous equilibrium. And really, it's not a huge difference between the two. Just remember, in the actual equilibrium expression, all you can have are gases and aqueous things. You're not going to have solids or liquids. And that really applies to both situations. But when you're looking at homogeneous, they're all gases that are all aqueous. But when we got into heterogeneous situations, we could have some solids and liquids in there as well. And remember, they're technically a part of the expression, but they're going to be over with a constant, not to the right of the equal sign where our variables are. And also know how to convert back and forth between Kc and Kp. Sample problem 15.2 gets into that, and we've looked at that in numerous problems in the homework. So be able to convert back and forth between the two. Know the meaning of the magnitude of Kq. Magnitude is always how big is the value. So what is the value? Remember, when it's much greater than 1, that means you are favoring the products. When it's much less than 1, you're favoring the reactants. And there are situations where we can look at how K is changing and to say we're either shifting towards reactants or products. That's related to this idea as well. Remember, what it comes down to is it's products on top and reactants on bottom. And because of that, when K is large, that means products are bigger than reactant concentrations. When K is very small, that would mean reactants are smaller than products. And for the same system, changing temperature and how that affects K, you can literally see by the growth in K how much more you're shifting towards products, or the drop in K, how much more you're shifting towards reactants. Also be able to manipulate. Remember I said there will be one of these questions on the test, or I should say at least one of these questions each on the test, and also be able to handle when you're doing multiples of them. So be able to figure out when I multiply by a constant what that does. Remember, raised to the power of that constant. If I'm, oops, I wrote that by the wrong one because the first one listed here was reversing the reaction. And when you reverse the reaction, you flip your reactants and products. That's going to be an inverse situation. When you are, well, actually, I did do that right. Multiplying by a constant, that was the first one there. So whatever it used to be, you're going to raise it to some new power when you multiply by something. And then the adding, remember, when you add reactants, that doesn't add Ks, it multiplies Ks. And then be able to handle combinations of each of those. Next, solving for KQ. If you know the equilibrium concentrations, write the KEQ expression from the reaction, plug in your equilibrium concentrations, and you've got your KQ, you're done. Now, if you know initial conditions and either one of the substances equilibrium or one of the changes, in your icebox table, when you set up your x's, you'll be able to calculate what all the x's equal in a very, very quick calculation. And something like sample problem 15.9 would be similar to this. So when you set up your icebox and you're able to determine x without doing any fancy math, just by simple subtraction addition type things, then you can establish what your equilibrium concentrations are, get rid of the x value, and plug in and solve for KQ once again. So a couple different situations here to handle. When they flat out give the equilibrium concentrations, and when you have to use your icebox to do some simple math to figure it out. Next thing, solving for equilibrium concentrations if you know the KQ. These are the typical ones that are a little bit more problems. These are where often you have x's and you can end up with having to do the quadratic equation. But the reality is there's often ways around that. Depending on what they give you, you may have enough to actually plug in and calculate what the equilibriums are without having to set up a whole KEQ solve for unknown x. So when you look at your setup, if you only have one unknown, it's very easy given the KQ expression and the given KQ to solve for what that unknown concentration is. Um, and if you know KQ and initial concentrations, how you go about doing that. Sample quantum 15.12 and 655 exercise page can help you look at those situations. And then finally, quadratic equation. In the notes, we did this twice. Equilibrium problem 1 and then the Q problem. Both of those we looked at how you would end up with the quadratic form of the equation and then using the quadratic equation, solve for x. That's something that you'll have to do at least one problem on the test. The trickiest problem on the test involves that quadratic setup. Okay, next, predicting the direction of a reaction shift to reach equilibrium. In other words, what's happening? Am I shifting towards the left or shifting towards the right as I approach equilibrium? Well, sometimes you don't really know if you're at equilibrium or not. So if you're given concentrations, you're not sure if they're equilibrium concentrations, plug it into the equilibrium expression and solve for what we call Q. And if you compare Q to K, you can see which way equilibrium is going to shift. But if you recall what I said, the easiest way to do this is to look at it in the alphabetical order. And the reason why that makes it so much easier is we can then make these things arrows. And if we know K is greater than Q, you know that we are going to be shifting to the right. So we're left of equilibrium. In order to achieve equilibrium, we got to move to the right and make products. And if K was less than Q, then we have to shift to the left. In other words, to achieve equilibrium, we had to increase our reactant concentrations and decrease our product concentration. So this is a much better way to look at K and Q. And then remember, this is something that is an application of Q. So not only can you tell whether you're at equilibrium, which way you're going to shift to achieve equilibrium, but if we've got a difficult icebox problem because we didn't have, a value here and these were 0, let's say we had values in each position. How do we know whether we're going to be shifting to the left or the right? Well, we can actually do this, and that'll tell us whether we're shifting towards reactants or products. Because if we're shifting towards the reactants, that means we're going to have plus on our reactant side and minus on our product sides, and vice versa. If we're shifting towards the products, that means we're going to have a plus on this side and a minus on that side from an X point of view. So that is one of our applications of Q. Le Chatelier's principle, one, you should understand exactly what it means. So what are things like a stress, and what is Le Chatelier talking about when you stress a system? And you should also understand why closed equilibrium systems are self-correcting. That's something we went through in class and looked at. Know which direction, if any, of the following conditions will shift equilibrium. Because remember, things like a catalyst have no effect on equilibrium. And in pressure volume situations, if there's the same number of gaseous moles on each side, there will be no shift in equilibrium because you're not stressing the system. Know what each does to the actual forward and reverse rate. So it's not just enough to be able to predict left or right. Know what that means in terms of whether you're affecting the forward rate or the reverse rate or making it bigger or smaller to cause that shift left or right. And then know what each does to the value of K. So these are the actual things that can change it. Really know exactly what they do. And then some general terminology thing. Know what is equal at equilibrium. Know what is constant at equilibrium. Don't confuse those two. Don't confuse a shift to the left with saying that the left is favored. If equilibrium is shifting to the left, that just means as we reach equilibrium, we're increasing our amount of reactants and decreasing the amount of products. It doesn't mean we will have more reactants than products. That depends on the actual value of K. So know what they mean. So how are they similar? And know how they're different. We're talking about a shift to the left or saying the left is favored. Be careful of those two terms. And that finishes my test help movie to help get ready for the equilibrium test.